Well, good afternoon. It's that time again, time for our course on Bayesian PK-PD modeling. What I'm going to do here is just recapitulate a couple of slides that we had before, and then move on to talking more about computation for Bayesian modeling. I guess before I start, I'll just do a quick query here, see if there's any questions that you want to ask before we get started. I'll take a minute and keep an eye out for questions here, and then we'll get rolling. Okay, don't see anything coming along here, so why don't I go ahead and get started. Just remind you sort of where we left off the last time. I had started out sort of giving you what I saw as potentially the bad news to doing Bayesian modeling. Namely some computational problems that arise when we try to construct and make inferences from these posterior distributions. So let me just sort of recapitulate that. So suppose that you've selected a distribution for both your prior, that's our, recall that again, that's our P of theta, so that's our prior distribution and our parameters theta. And we've got our likelihood here, our P of y given theta. Y being our vector of data. So, and let's suppose that theta here is a vector of 6 parameters and y is a vector of, let's say, 200 observations. And let's say I'd like to estimate the expected value of some function of my parameters here, which I've just written out here then as the expected value of some function of our parameters given the data. In other words, I need to sort of construct the posterior distribution for that function and then take the expected value. Well, suppose of course I know from my Bayesian theory here that that posterior distribution is proportional to the product of my likelihood function and my posterior distribution. So I can plug in those relationships here in order to construct my my posterior. So you can see here I'm just saying the expected value then I get by taking the function, taking my posterior, and then integrating over all of the parameters in here. The only thing that's happening when I move over the right hand side is now I've written my posterior in terms of taking into account it's proportional to my likelihood and my prior in here, so I've got this 6-dimensional integral to take care of. So the question is, well, okay, how do I do that? Well, if I'm lucky, then those integrals have known analytic solutions, but that's pretty rare for PK-PD modeling applications. And then for integrals in fewer dimensions, say up to around 3, a numerical quadrature method might be practical. I might even be able to push it to a few more dimensions than that, depending upon the machine I'm sticking it on. But even so, 6 dimensions is pushing it, and may not be feasible depending upon the system I'm working with. And then now imagine a situation that's more consistent with the kinds of problems that we often do with population PK. Suppose we've got a population PK model that has a bunch of individual specific parameters in there on top of the population parameters. Then we might be talking about a total number of parameters in the hundreds or maybe even thousands. So now I've got to take an integral over over something with dimensions in the hundreds. And so we now have a situation where quadrature is certainly no longer a viable option for that problem. So what do I do? And it's in fact that very kind of problem that held up the use of Bayesian methods for a lot of practical applications, are just those sorts of computational problems. And before I give you the way out of this morass here, I should double check here and make sure that people are actually hearing me here. Of course, if I ask this question verbally, I might not get an answer if you're not. I guess Joe or somebody, if you could just put a quick thing on there just to indicate whether the audio is okay. Okay, then we're on our way. Okay, well, the hope here is something called posterior simulation. In other words, simulation from the posterior distributions for our models. So the question here then is what if I could simulate samples of my parameters theta from the joint posterior distribution? Excuse me, somebody's making little noises at me. Let me double check real quick. And don't know what it is, so I will ignore it. Oh, it's probably some noise from Windows. Okay, excuse me. Okay, so let's say I could simulate, get a random sample from my posterior distribution, and this is the joint posterior distribution across, all of the elements of that vector theta. Then I could estimate my expected value for that function of theta then by the arithmetic mean. In other words, I would just take all of the samples that I generate for my thetas, apply the function to it, sum over that, divide by the number of samples I've taken, and that would then give me an estimate of that expected value. So that might be a good solution if I could do that. And the question is how do I do that? How can I simulate samples from a very high dimensional joint posterior distribution, assuming I can even construct the posterior distribution in the first place? And the answer that we're going to use for that is something called Markov chain Monte Carlo simulation, or what I'll generally refer to then as MCMC simulation. And in particular, we're going to do Markov chain Monte Carlo simulation using the software package WinBUGS. So that's what we're going to be doing throughout the course. A little later, I'll touch upon some other software that's available for also doing that. But for now, let's focus on WinBUGS. And then suppose that I can do that using something like MCMC. How do I make inferences then from these posterior simulations? One I've already alluded to is how you might get the expected value of some function of my parameters. But we can go past just expected values. We can describe entire distributions of those functions. So when we do our posterior simulation then from our joint posterior distribution, what you get then are vectors of parameters that you can work with. You can also use those simulated parameters then to do predictions, which also then represent posterior predictions, or the posterior distributions of those predicted values. So you can get those whole collections, but in a number of situations, what we'd really like to do is make inferences about the individual parameters, and to do that we need to talk in terms of the marginal distributions, in other words, marginal posterior distributions, not joint posterior distributions. And how do we do that? Well, let's start out with the notion here that if I want to describe the posterior distribution of any scalar function of the parameters, what I would do is I would take each individual vector that I simulate from my joint posterior distribution, apply the function to that, and then I would do that for each one of those sampled vectors, and that would then give me a distribution of the function of those parameters. And in particular, that empirical distribution, in other words, the distribution of those simulated values, then that empirical distribution approximates the actual continuous posterior distribution. So I can do that for any function of theta. Well, if I want to talk about any single parameter in that vector theta, well, to get that out is really just a special case of this notion of doing a function. That would just be the simple function that selects for one of those parameters, and similarly I can just take any one of them and take a look at its empirical distribution, and that too would then describe the marginal distribution for that individual parameter. And once I have that marginal distribution for that parameter, then my inferences then are just based upon things like moments of that. For instance, the posterior mean or mode or the posterior standard deviation and such. I can work with that. I can work with things like probabilities based upon that empirical distribution, or percentiles from that. In fact, I mentioned median in a way in the context of moments. That was actually incorrect. The median is actually a percentile. But I can generate any of those from my marginal posterior distribution, or more correctly, I can generate from my samples, and those would approximate then the corresponding moments, probabilities, or percentiles for the true posterior distribution. And again, they're readily estimated just by doing the corresponding sample statistics based upon those simulated values. And that's largely how we're going to be operating throughout the course then, is we're going to be using a Markov chain Monte Carlo simulation technique to generate samples from our posterior distribution, and then we're going to use those samples in order to make inferences about the various parameters in the model, and in turn to make inferences about predicted values based upon the model. Let's see, somebody's asking me to explain something. Let's see if I can get to see the whole question. What I mean by joint posterior distribution. Okay, question is what do I mean by this joint posterior distribution? I'm trying to think if there's a good thing I could use for a quick example. Well, let's just use a typical two-parameter distribution that we commonly use, namely a normal distribution so let's just take let's say we have a normal distribution which has parameters of a mean and a variance, and let's just call them mu and sigma squared. So I'm just starting out thinking about, let's say let's say our likelihood function is that normal distribution, and both our mu and our sigma squared are unknown parameters. So we've got two unknown parameters. If we're going to do some inference given, let's say, a random sample of data, or a data that we think is a random sample from that distribution, and we would specify some prior distribution for both our mean and our variance. We could construct a posterior, and now this posterior in here, in fact, let's maybe step back to, let's get something that actually shows, well, here I can just use this. So in other words, I'm saying this P of y given theta is a normal distribution. Theta now represents this pair of parameters, a mean and a variance. Similarly, my prior then is actually a prior distribution for both of those parameters. If I think they're independent, it would simply be a product of a prior for the mu and a prior for the sigma squared. And then from that I would get a posterior distribution for my parameters, which again are a pair of parameters. So actually in this case, both the prior and the posterior are a two-dimensional probability distribution, because I've got that theta is a vector of two values. So in both cases we're talking about a joint distribution, joint in the sense it's jointly describing the probability distributions of mu and sigma squared. So I'm not sure if that clarified it, but hopefully it does. So we're talking about a situation where we're describing simultaneously the probability distributions for multiple quantities. And the example I just gave, then it would be a joint distribution then, or a two-dimensional distribution describing the probabilities for mu and sigma squared. If you were to actually plot such a thing, you actually have to use a three-dimensional plot to actually describe that bivariate distribution in this instance in order to see it. And I guess the corollary question on that then is, what is a marginal distribution? And the marginal distribution would then be the univariate distribution describing the distribution of only one of those parameters. Okay, let's see, is that where I was? Yeah, okay. So we've just sort of quickly described the notion of then making inferences from posterior simulations. So if we can simulate these things, we can make inferences then about the true posterior distributions. And let's talk a bit about, the tools that we need for doing that. So just comment here, I say a recent development then of more flexible methods and computational tools, namely tools like Markov chain Monte Carlo simulation, have made it possible to do this. And I say recent, it's maybe not quite as recent as probably when I first wrote that statement, but most of the work on Markov chain Monte Carlo simulation has occurred since, I forget when probably the most key papers were off the top of my head, but I think the bulk of the work has been since 1990, let's say. And anyway, given tools like MCMC, it's now possible to model quite complex nonlinear systems, like PK/PD models, and even fairly complicated processes like, entire clinical trials. And so we can model those things and simulate those things based upon the posterior distributions we get. Now, just briefly, a qualitative statement about what Markov chain Monte Carlo simulation is. We're talking about simulation methods for performing high-dimensional integration that's required for Bayesian modeling. In other words, they allow us to simulate from high-dimensional probability distributions. So you can deal with situations now where you may have tens or hundreds of parameters incorporated in your model, thus resulting in multivariate posterior distributions that have that number of dimensions in them. They allow you to simulate random variables from posterior distributions of interest. So that might be things like means and variance of population distributions of PK/PD parameters. And then the inferences follow directly from those distributions. So we take the distributions of the simulated parameter values. In other words, we're talking about posterior simulations again. We can generate point estimates for our parameters based on things like means, medians, or modes of those simulated posteriors. And we can generate the Bayesian analog of confidence intervals, which are generally called credible intervals in the Bayesian context, and we can generate those from things like the 2.5 and 97.5 percentiles of those simulated values. So a little more then on MCMC. First, it involves random draws from approximate distributions. By approximate, I mean we're going to take a distribution that in some sense approximates the posterior distribution that we actually want to sample from, and then we correct those draws iteratively in order to better approximate that joint posterior distribution we're trying to simulate from. Now, the way the samples are drawn, they're drawn sequentially, so that each draw from that distribution depends upon the previous one, thus forming a Markov chain. And eventually that Markov chain converges to something that's called a stationary distribution, which generates samples that are equivalent to those generated from the joint posterior distribution. So that's the sort of, again, the fairly, in qualitative terms, the basic premise. We start out with what is commonly termed some sort of proposal distribution that we draw from, and then we modify that as we go along, and there's, as a result, there's a convergence process of sorts that we'll discuss later. The samples are drawn in a way where one sample depends in some way on the previous one, so a Markov chain is being formed. In other words, the samples are not independent random samples, but eventually that collection of samples from that Markov chain converges to a stationary distribution that's equivalent to the joint posterior. There's a number of algorithms under the heading of MCMC. The two most common, fairly broad categories are the Metropolis-Hastings algorithm and Gibbs sampling. In fact, actually, even Gibbs sampling it can be described as a special case of the Metropolis-Hastings algorithm. Some issues here. I already mentioned that the MCMC samples are not independent of each other. They're actually serially correlated. And one consequence of that is that inferences based on MCMC require more samples than would be required for independent sampling. In other words, you need more in order to get the same precision. And then practical consequences of that, of both that and the convergence process here is, one, you only want to use samples that are drawn after convergence is achieved. In other words, you would discard earlier samples, and we commonly refer to those we discard as a burn-in phase in the MCMC process. And we want to draw more samples than you would for independent random draws in order to get the same precision. It also means we have to think about issues of convergence, for example, when we evaluate the results of what we're working with, and we'll talk more about the specifics of that shortly. And we also have to somehow figure out, okay, yeah, we know we need to draw more than we would for independent random draws. The question is how many more, and how might we judge that? And again, we'll spend some time on that. Let's give you a handle on one of these algorithms. It's one of the easier ones to describe. It's also, let's see, I see there's another question. I'll get that in just a second. What I'll talk about first is something called Gibbs sampling. One, it's one of the easier ones to describe, but two, it's important to us because the primary algorithm that's used by WinBUGS is in fact Gibbs sampling. So more on that in a minute. Let's see, I've got a question here. It says, can we choose algorithms in WinBUGS, and do algorithms make any meaningful differences? Well, we'll talk a bit more about what's going on under the hood in WinBUGS. The short answer is it's actually hard to give a real short answer until you understand the algorithms used in WinBUGS. WinBUGS is definitely a Gibbs sampler, so in particular you cannot choose to use a general multivariate Metropolis-Hastings algorithm in WinBUGS. But there are some choices that you have in terms of how the Gibbs sampling algorithm it uses and how that will proceed. So your choices are limited. It has to be within the framework of Gibbs sampling. And then the question is, do algorithms make any meaningful differences? And the short answer to that is yes. We'll see as we talk later, as we look at some examples in particular, that, for instance, I make mentions of the convergence process and how many samples that you need. What type of algorithm you use will influence things like how quickly convergence is achieved. It may also influence the degree of autocorrelation in your samples, which in turn will influence how many samples that you'll need in order to get adequate precision. And finally, it can certainly have an influence on the speed of computation. So yes, it can certainly make a difference. Let's talk a little bit about Gibbs sampling. Again, that's the algorithm that is used by BUGS. In fact, I can't remember if I had mentioned on Friday what the fact that BUGS is actually an acronym for Bayesian analysis using Gibbs sampling. So let me describe it in fairly simple terms. And the trick here is we want to use a technique here that will take us from a difficult to work with multivariate sampling problem and convert it to a sequence of univariate sampling problems. and in general univariate sampling problems are easier ones to deal with. So how could I construct a Markov chain based upon some sort of sequence of univariate samples? And that's the idea here. So what I'm going to do is I'm going to construct this convergent Markov chain. It turns out I can do that by progressively sampling from something which is commonly termed univariate full conditional distributions. And let me get your head around that before I actually describe the algorithm. Okay, again, let's assume that we've got some model where we've got a parameter vector theta which has n elements in it. So there's n scalar values then that make up this overall vector theta. And so what I want to do is construct a set of univariate distributions for each one of the parameters. So we'll use as our illustration the first one here. So I want to construct a probability distribution here that describes the posterior distribution of just one of the thetas, theta 1 in this case, conditioned on all of the other parameters as well as the data. Now it turns out that's not too hard to construct algebraically if you've already constructed the algebra for your posterior distribution. So if you've written out your posterior distribution, in other words, that would be P of where all of the thetas appear to the left of the conditioning bar here. If you take that, it turns out that this univariate full conditional distribution is actually proportional to it. So it's not identical because you would have to have a different normalizing constant in order to make this thing integrate to 1, which is necessary for it to be a probability distribution. But otherwise, it's identical. It has the same functional form in terms of all the components here. And it turns out that most of the sampling techniques that we're going to use, it's actually sufficient to know these distributions only up to a multiplicative constant. So that turns out not to be a big problem that you have different normalizing constants. So, but the short point here is just that once you have the algebraic form of the joint posterior distribution for all the parameters, getting the algebraic form then of the univariate full conditionals is a relatively easy problem. And the only difficulty is getting the appropriate normalizing constant. So you can do that then for all of the parameters. You can write out those univariate full conditionals for each one of the parameters conditioned on all of the remaining parameters in here. And then the Gibbs sampler, the way it works is you simply take well, first of all, you have to have a set of starting values. So for example, let's say I equals 1. So we're about to draw our first sample from a Gibbs sampler. The user would have to provide initial estimates for all of the parameters, or at least all of them except for one of them, in this case theta 1. So in that case, so our theta sub 2 0 here, so that would be our initial estimate for theta 2, same thing for theta 3, and so on up to theta n. So you provide the initial estimates, you plug those in, you plug in your data. That now gives you a probability distribution for theta 1. You draw a sample for that. So now this is theta sub 1 super 1 over here. So that's our first sample for that. Then we go down in order to get a sample for theta 2, we now plug in that number we just generated for theta 1, and for all the remaining parameters we still have the initial estimates. Okay, and we use that univariate distribution for theta 2 to generate a value there. And so now you're going to come down and plug in both your the new values of theta 1 and theta 2, but you still have all of the initial values for everything else, and we generate for theta 3 and so on until finally you get down to theta sub n, where now you've got for all of the parameters up to n minus 1, we have the first draw that we've taken. there. Again, we've got our data, and we generate finally our theta n for our first for I equals 1. And now that cycle through all of those is now our first draw from our Gibbs sampler. And then you take those values and you plug them right back in, and you go through that cycle over and over and over again. And that is what a Gibbs sampler is simply doing that, doing all these univariate samples in order to construct approximations of samples from the joint posterior distribution for all of those thetas. So again, the point is here we've reduced then that multivariate posterior sampling problem to a sequence of more manageable univariate sampling problems. And there's a fairly large host of algorithms out there for dealing with that univariate sampling problem for different kinds of distributions. And in fact, we'll spend a little bit of time today talking about some of those, or at least some of the ones that are used within BUGS. Let's see. It's somebody asked, does the order of theta matter? Yes, it can matter. The order in which Gibbs sampling proceeds can influence. It won't influence the final result as long as you've taken everything long enough to have convergence and so on. But it could influence the rate of convergence. It could influence the degree of autocorrelation and so on in the samples. So it could. So I guess the short answer is it could influence the efficiency of sampling. But trying to find an optimal order is not always an easy job. So let's make that more concrete, and let's actually do a specific example, a fairly simple one. So let's take a case where our data is actually a single observation from a bivariate normal distribution. So in other words, our y is going to be a pair of numbers, y1 and y2, that are going to come from a bivariate normal distribution. So mu here then is going to be it is also going to be a vector of two values. In here we've got a covariance matrix here, and to keep this real simple, we're actually going to assume we know it. Of course, that's not very realistic in most cases, but it's useful just to illustrate the basic notion of a Gibbs sampler. So our unknown parameter then is going to be this mu, which is going to be bivariate. Here we've got two values. So we want to use a Gibbs sampler then to get a posterior distribution for those two means. For now, I'm just going to use something termed an improper uniform prior on mu. And I should explain that because we haven't talked about that. Okay, uniform means that all possible values of mu are equally probable, but we're talking about the entire real line in this case, going from minus infinity to infinity, and for any non-zero value of probability, then that density does not integrate to 1, and that's why it's called improper. Now it turns out there's some situations where you can't get away with that, but for fairly simple models like this one, you can get away with specifying a so-called improper uniform prior on that. Alternatively, you could probably use a prior which is fairly flat but not improper, but for now we'll do it just to keep the algebra simple. So in other words, if you like, our P of theta is actually, in this case, it's actually a two-dimensional uniform. So you can think of it as a flat plane on two-dimensional real space, going from minus infinity to infinity in 2 dimensions here. But that's nothing more than multiplying. So now our P of theta is basically a constant, which we can then multiply times our likelihood, and basically then the prior our in a sense almost disappears. It doesn't play any significant role in the calculations. So anyway, it's fairly easy then to construct our joint posterior for for mu. It turns out that's actually just a normal distribution. It too is going to be a bivariate normal. And the conditional, the univariate conditional posterior distributions for mu1 and mu2 are also normal in this special case. And this just, I've written them out here, so the conditional distribution for mu1 given mu2 and the data is just, again, it's normal with the mean here equal to y1 plus our correlation times mu2 minus y2, and then we have a variance equal to 1 minus rho squared here, which is again our correlation here. We're assuming a variance of 1 for the individual items here. And then mu2 given mu1 and y is identical, except the role, you'll just notice that all the subscripts are reversed. So now here, wherever you saw a 1 up here, it's a 2 down here, and vice versa. So those are our univariate conditional distributions. And to do the calculation, then, to do our Gibbs sampler, we need to first specify an initial value for mu2, and of course we've got our data y1 and y2 in here, and we know our rho, so we go ahead and plug in our mu2, our y2, our rho, and we can then get we sample then from that normal distribution, and that gives us a sample for mu1, which we then plug in to our distribution for mu2. So we plug in our mu1, our new sampled value for mu1, we plug in our y1 and our rho squared, and we generate a value for mu2. And then we take that result, move back up, and we cycle through that process over and over again. And here I illustrate that using a simple R program, an R function I've shown here. So let's make it more specific. Let's put numbers on it. So let's say that y is just the origin. So y is just 0, 0, and rho is 0.8. And we're going to plug that in here. And as I say, for this simple case, the Gibbs sampling can be done with a very short R function. Also, I believe I've included in your in the USB drives we sent out here, you should find in the MI250 directory, there should be a function there called Gibbs.example.r, which contains this function as well as the other things needed in order to call it to do the Gibbs sampling. So our simple function here takes the number of samples that we want to do. It takes our data. It takes the variance matrix. And let's see, I believe for mu I have to put in, do I need to put in any initial estimates? Oh, mu init, yeah, sorry. Mu init will be our initial estimates for mu in here. So for the way we're going to actually do this here, so I'll take, what do we got? We're going to create mu is going to then be just a matrix that's going to hold our results here. I initialize mu to my mu. So my first, basically my first row of mu is going to be my initial estimates, and then I go through and loop over that process we just talked about. I generate a mu1 first using the initial estimates, then generate a mu2, then I use the results from that, and I come right back up and do this over and over and cycle through that process until I get to the number of samples I specified, and it'll return the resulting matrix, which in this case will be, yeah, I guess I'm going to have 2 columns representing the 2 elements of mu, and the rows correspond to the different MCMC samples. It's taking a second to update this picture for some reason. And this just illustrates this for the case where what I did is I took that function and I specified 4 different starting points. So you can see here I've got a starting point here, which is what is it? It's looks like it's minus. Looks like this one is minus 2.5 and 2.5. I think that's what I used. If you look at the this, I think came right from the function I sent you, so you could see what I actually used, but I think that's the numbers that are in there, and then I basically did a square here. Nothing magical about it. I just picked numbers that were pretty far enough apart relative to what I wanted to look at, that you could see the convergence process. So here, for example, you've got 2.5, 2.5, and what is this, 2.5 minus 2.5, and so on in here. And this is just showing after the first 10 samples. Now for this very simple model, it actually converges quite quickly. So you can see a couple of the points are actually pretty far away from the main distribution, but even for those, it pretty quickly came into line here. So after 10 iterations, we're actually probably converged, though I actually don't know that until I do more of them. But then you can see after I do 1,000 samples, you get a nice bivariate normal distribution, which is what we should be getting. So again, you can see it converge quickly. But one of the points I'm illustrating here that we'll talk about when we start talking about more about convergence and how you test for convergence is doing exactly this kind of a thing, where I use different starting points and test whether or not each chain whether the chains come together and seem to describe a common distribution. So that's a very simple Gibbs sampler. Now of course that's only a bivariate for a bivariate posterior distribution. In most of our problems we're going to be dealing with something a lot messier than that. Okay, so now let's see. This one I already covered back on Friday in terms of the WinBUGs, but maybe I'll use this as a lead-in for what I want to talk about next, which is to give you a little bit more information about some of the things that are going on under the hood with WinBUGs. So why don't we actually start with this slide anyway. It's a good one to lead into that. So just a reminder about WinBUGs, what it is. I actually mentioned again today that the bugs part of the name is actually an acronym meaning Bayesian analysis using Gibbs sampling. It's a nice versatile program for doing Bayesian modeling using Gibbs sampling. I spent some time with you last time talking about the text model specification and a bit about the data format. I won't spend any time on that today, but the thing I do want to lead into is to talk about the methods that are occurring inside WinBUGs. As the name implies, it uses Gibbs sampling, where it samples from the conditional distributions, usually univariate conditional distributions, though there are some situations where it may do some block sampling of multiple parameters, but about the only place where it does that in the case of WinBUGs is when that joint posterior distribution, where if the joint distribution, the joint conditional distribution for them is a multivariate normal. In that special case, it'll do block sampling. But for the most part, it's going to be sampling from univariate distributions when it does the Gibbs sampling. And it has an algorithm inside where it attempts to decide what is in some sense an optimal algorithm to use for the univariate sampling. Now in some cases, WinBUGs will be able to discover that certain elements within the model are actually conjugate, are using conjugate prior likelihood combinations. Those are situations where the posterior and the prior have the same are from the same family of distributions. So for example, in the example we just did, everything was normal. The prior was normal, I'll just say the prior was normal, the likelihood was normal, and the posterior was normal. And under those circumstances, we say that we have a conjugate system, and in which case you can take advantage of the fact that you know what the form of the distribution is, and you can use standard algorithms for dealing with it. And in particular, there are standard algorithms for things like normal distribution, chi-squared, gamma, and a few others. So if WinBUGS can figure out that it's actually dealing with a conjugate system, it'll do that. So that would be its first choice if it can do that, because that would be the fastest. The next step it would go is it will ask, okay, can it tell whether or not that univariate conditional distribution is log concave? Or put another way, log concave means that the log of the density is concave. If that's true, it uses something called a derivative-free adaptive rejection sampling method, which again is a fairly fairly efficient algorithm that it can run pretty quickly in cases like this where it doesn't really know, it doesn't have a specially constructed distribution, but this gives it a way of fairly efficiently dealing with a distribution that it doesn't know, it doesn't have a sort of a built-in algorithm for. Another situation where it can simplify it somewhat is if the range of the distribution, in other words, the support, the values that the random variable can take, if they're restricted over a certain range, then it uses something called slice sampling as the method. And then finally, if it can't discover that it has any of those properties, it cries uncle and says, okay, I'll just do Metropolis sampling, which is essentially a univariate Metropolis-Hastings sampling strategy, which would be the slowest of the bunch in here. So it makes an effort to try and optimize that selection process. By the way, what I just said there all applied to the continuous distributions. In the case where it's dealing with discrete distributions, in most cases it uses a relatively simple inversion problem. Now that's only applicable if there's a finite upper bound in here. If it's dealing with something within the Poisson class of distributions, which do not have finite upper bounds, turns out there are some well-developed standard algorithms for dealing with that, so that doesn't cause it any particular grief in here. So that gives you an idea of sort of what's going on under the hood for these. And in fact, the next step I wanted to take is actually spend a bit of time going over some of those algorithms. So let me scoot past the stuff we did on Friday. Okay, well this is just a reiteration of what I just talked about here. And I wanted to spend a little bit of time talking about random variable generation, particularly as it's relevant to WinBUGS. And I guess the starting point here is to mention that at the core of almost all random variable generation algorithms is going to be a uniform pseudo-random number generator. In other words, this is an algorithm that produces a deterministic sequence of numbers. In other words, they're not truly random. It's a deterministic sequence of numbers that have the properties of an independent sample of uniform 0-1 random variables. In other words, they're not truly random, but they mimic random samples. And I'm going to skip the algorithmic details on that. Maybe if we were talking 30 years ago, it might have been worth the trouble to talk about it, because there were still a few sort of poor algorithms out there that were still in moderately common use. But at this point, pretty much all the statistical software packages you're going to run into include a well-behaved uniform random number generator, so I won't spend any time on that. If anybody's dying to look at the guts of those things, I can certainly direct you to some references that talk about the algorithms for uniform random number generators. But for the most part, let's just take that this uniform pseudo-random number generator is a given in here. So let's talk about probably the simplest to describe and perhaps most common way of dealing with sampling from a univariate distribution, and that's to make use of the inverse transform, assuming we can construct it. So what we're talking about is, let's say I want to generate some random variable, we'll call it x, from a distribution that has a cumulative distribution function, capital F here. So, and the way I would do that is, first I start by generating a uniform random variable. So I'm going to generate this variable here, I'll just call it u, from a uniform 0, 1 distribution. So that's coming from our, so we're going to do that from our pseudo-random number generator. And then in order to get a random variable x, which is distributed according to this distribution I'm actually interested in, I have to construct an inverse of f. So I have to take my distribution, and let's use this picture here to describe this in the continuous case. So let's say I've got some distribution. I know its cumulative distribution function, and that I've described it right here with this blue curve. It happens that the one I've drawn here is the cumulative distribution function for the standard normal distribution. So I've got that, and let's say I've drawn that, my uniform random variable u, and let's say it happens to be 0.653. And the way I would get the inverse of that, in other words, do this task, I'm going to take my inverse of f, I'm going to plug that value u into that inverse function, and that's going to give me this x value that I want. So all I'm going to do here is take my u, and if I put that on the y-axis here, go over to just go over horizontally to my cumulative distribution function and read off the corresponding x value, which in this case happens to be 0.393. That then is now going to be a random variable distributed according to this distribution f. So that's one of the most common ways then that we deal with generating random numbers from some arbitrary univariate distribution as opposed to the uniform. And the key here is I have to have that uniform random number generator in order to do it, and I have to have and f has to be defined in such a way that I can actually estimate what its inverse is. Now I did that for the continuous. Turns out for the discrete it's not that bad. It's actually tougher to write out the algebra, but graphically it's pretty much the same picture. In fact, what I've done here is I've shown the cumulative distribution function for a, say I'm trying to remember, this was a binomial distribution, and I forget what the probability was that was used in it, but it's a binomial distribution with up to 5 possible values here, and so it's described with a discrete one. The CDF is described with us in terms of a stair-step like function, and let's suppose I'm using the same u here, 0.653. Again, I just go right over until I smack into my function here, and then go right on down to the axis, and in this case it gives me a 3 when my u is 0.653. So that for both cases here, the inverse transform works fine for both the continuous and discrete random variable cases. So that's something that if you weren't already familiar with doing this, I would sort of keep that in your back pocket when you're doing a lot of simulation problems. I've found it useful to actually construct these in a number of situations, particularly when I've been dealing with things like discrete random variables. So that's one of the more common types of ways that we would deal with the problem. And recall back up here when I mentioned this idea of where for discrete distributions within WinBUGS, the first choice, if it's got a finite upper bound, would be to do inversion. And when I said inversion, I meant exactly the process I described here. Okay, so that's one of our easiest ones. Another category of sampler out there is something called rejection sampling, and I'll give you, this is sort of the simple case of rejection sampling. Again, let me flip back to the thing here. Where I'm leading to is this algorithm here, the adaptive rejection sampler that WinBUGS uses, which is a little bit more complicated, but it's easiest to explain that if you first understand what a simple rejection sampler is. Okay, and let me give you that. So rejection sampling, again, suppose let's say I've got some distribution with density f, and again I'm still assuming univariate right now to keep things simple. So little f is now representing the probability density function that I want to sample from, and I'm going to generate some value x from that density. Well, the first thing I have to do to use a rejection sampler is I have to pick some other density. Now the idea here is that, let's say f is something for which I do not have a built-in sampler. I don't have an easy algorithm for sampling from it. So what I'm going to do is I start out by picking some distribution for which I do have an efficient algorithm. You know, it might be something like a normal distribution, for example, or some flavor of a t-distribution or something like that. And I'm going to select a density such that the density I want to sample from is going to be less than or equal to that g of x times some constant, which has to be bigger than 1. Okay, so if I can find a density for which this statement is true for some m bigger than 1 and for all x, then I can do this method. And of course that's the dirty detail here, is you have to be able to well, typically what you actually end up doing is you probably pick a g and see if you can find an appropriate m. In some cases that m may not exist for particularly nasty problems, but more often what you'll do is you'll pick a convenient g and then figure out what m makes this statement true. Okay, so that has to be true, and you have to find such an m because you're actually going to use it in the calculations. Once you have those, then you would generate a random variable that we'll call y from that distribution g. You also generate a uniform random variable, so you're generating u from our uniform 0, 1 distribution. Then there's a test here. It turns, if that u is less than or equal this ratio, where I take the y I generated, plug it into that density function f. I also plug it back into my density function g and multiply that by m. I take that ratio, and if u is less than or equal to that, I accept y. If it's not, I reject y. And the way this works is, if I accept y, then I stop the loop and I accept y and call it x, basically. So I return, so that becomes my new x that I wanted to generate. On the other hand, if I reject y, I repeat this thing. I go back and I generate a new y and a new u and try again. And I keep on doing that until I finally get an accepted y. And of course, this is likely to be embedded in a bigger loop where I'm probably going to generate multiple x's in this process. So that's your basic rejection sampler, sometimes called an accept-reject algorithm. And so that's the simple case. Now, one of the stinkers here that we're often dealing with when we've got pretty complicated models is sometimes the function f here is going to be an expensive function to calculate. Looks like there's a question or more here that I didn't spot. Let me see what we've got before I jump in there. Let's see. I'm getting the word that we've got an audio problem. Okay, well, Joe says it sounds fine now. Okay, let's see where we were. I guess one question is where's best to pick up from here. Let's see. That happened certainly during the discussion on rejection sampling. So let me pose a quick question anybody can answer here is, should I repeat the entire discussion on rejection sampling or start somewhere in the middle? Okay, I got middle here. Okay, well, let's see. I'm trying to figure where the best middle is here. So presumably you got the idea. You have to pick a density and a value m such that this statement is true, that that f of x is less than or equal to m times g of x here for all x. And once you do that, then you go ahead, you generate a value y from g and a value u from our uniform 0, 1. You test whether or not that uniform 0, 1 variable is less than or equal to this ratio. If it is, you accept y and you assign it to x and you move on to your next sample. If not, you reject y and you repeat the process and start over. Okay, so that's our simple case. So let's go ahead and go to a little bit more complicated case that deals with the problem that happens with situations, well, where f may be difficult to calculate. Could be one situation. Another situation might be one where maybe finding the appropriate g and m might be difficult, because this technique will sort of choose the G and M for you, in effect, in this adaptive rejection sampling. And again, this is the algorithm that BUGS often uses, but it only works in the special case where our density function here is log concave. And again, that means where the log of the function, log of that density, is concave. Now, it turns out that if it's concave, if you have a function that's concave, then if you say pick a sequence of points along the x-axis, so again it's the log. So in fact, we'll start working with the figure a bit here. So the plot here is of the log of our density function, and it's this curved line right here, this curve that is the log there. Now, if it's concave, then if I pick a sequence of points along here and connect the dots, then that piecewise linear curve that you construct there will all be enclosed under that curved function if it's concave. If it's not concave, that won't be true. So in the case where it's concave, we're going to take advantage of the fact that that piecewise linear function is completely enclosed under the curve. So here's what we're going to do then. So if log of f is concave, then we can construct piecewise linear lower and upper envelopes of the log of that density function. So what we're going to do is we start out, we're going to take a sequence of values along the x-axis, so a discrete sequence of values, and here we're just calling it S sub n. So it's a set of n x values in increasing order. And actually, I'm sorry, it's actually slightly more than that. It's really, you also have an x0 and an xn plus 1 in here, so it's actually sort of n plus 2 values total, but in here. And in the formal method, there's actually formal ways of how you get the first and the last one, so your real choices are only the ones in the middle. Anyway, so you pick that sequence of values. They all have to be in the support of f. In other words, they have to be values of x such that f is non-zero. You then construct this function that I've called here the log of f underscore n. So, and that's going to be a piecewise linear lower envelope of our log f. And you construct that by just taking all of those points along here. You take the x values, you calculate the values of the log of f of x, and I see I have a typo right here. This should, I probably can't write this very well, but that should be log of f of x right there. So you take that, and so you have those points, and you can see how they're constructed for the example here, on here, and you connect the dots to construct that f underscore n here, that lower envelope for log of f in here. And then we can also construct an upper envelope, and we're going to call that f over bar n. So get the log of f over bar n. Again, it's going to be piecewise linear in this case, but the trick we use for that is sort of by extending and intersecting all of the secants that are created to construct the original function. So for example, you can see here we've got this piecewise linear part from our lower envelope, but then if you extend that outside the function, it's right here. You know, on the top, also down here, it extends below on that. So that's part of it. And then we have another one here that's constructed from this other line right here. So that's right here and here, extending outwards. And similarly, we have this line here, which goes right there and there. And the other part that we have to work with is so when we finally get over to here where we match up with this, we just drop a perpendicular right here. Same thing here. In order to create an envelope here, to get from this point to this point here, we just drop a vertical right here to construct the outer envelope there. So we're going to be working with those. So we've got an upper envelope, our log f over bar n, and a lower envelope here, log f underscore n. So that's what we're going to be working with here in order to construct this adaptive rejection thing. But right now we've just kind of defined the pieces of it. So now let's see how we construct an algorithm around that. So again, we're going to want to generate some random variable x distributed according to our density f, but we're going to restrict f to be log concave. We initialize that set of increasing x values that we called s sub n, and then we're going to define a density that we're going to call g sub n, and it's actually just going to be proportional to our f over bar n. So remind you again that f over bar n is this funny looking thing on top. It's the upper envelope of our function here. And we construct a density by dividing that by a suitable normalization constant that makes g a proper density. In other words, a density that it has to be a function that integrates to 1. And that I've just written. This is just a statement to that effect. So m is nothing more than that suitable normalization constant in there. So again, g of n is proportional to that f sub n. So we've come up with a recipe now for getting a suitable g and a suitable m for doing a rejection sampling strategy. So we start out, first of all, we generate a y from that g sub n. We generate a u from our uniform 0, 1 distribution. Now this rule is a little bit different here because instead of putting an f of y in this ratio here, we put an f sub n. So this is our lower envelope here. So if u is less than or equal to the ratio where we take our lower envelope function and a function of y, and then down here it's m times our g of n of y, then we would accept y. The reason for doing that is if you've got a density that's, say, expensive to calculate. Let's say we're dealing with a PKPD model, which is a system of several differential equations. So F involves solving that set of differential equations. It would be cheaper to calculate this f sub n of y once we've constructed it than it would be to calculate the f of y. So we might be able to get away with doing that. So if this is true, you would accept y and you jump right down and assign that value of y to the x that you wanted. Now if you can't accept y, if this is not true, then you have a secondary test where you actually do calculate the f of y itself in here and do the sort of the standard test from a rejection sampling method. And again, if it's true there, you accept y. And then if that's not true, then finally you reject y and you start over and resample again in here. And when you get to the very end of this, and this is kind of where the adaptive element ends up being in here, when you get to the end, you actually update your set of x's by adding to that the new x that you've just sampled, and reconstruct that, and then you go all the way back up to the first step here. Well, of course, now you don't initialize s sub n; you've already got it. But now you generate a g sub n minus 1 and so on and go through the process again. So as you move forward, you improve the degree to which your g of n is approximating the true distribution that you're trying to work with. And as you do that, you're more likely to be accepting y in here, and you'll have fewer rejections as you move forward through the algorithm. So that's, in short terms, one of the algorithms then that WinBUGS uses, but again, only if WinBUGS can tell that the distribution is log concave. And I guess what I haven't said is a lot of distributions are. So for example, a normal distribution is log concave. T distributions with a reasonably large number of degrees of freedom are log concave. So, but a lot of distributions that you regularly work with are, but there are some that aren't. And in particular, if distributions are kind of fat-tailed, they will often not be log concave. So the classic case there, for example, would be the Cauchy distribution, which is equivalent to the T with 1 degree of freedom. And I don't know exactly where the break is, but T distributions with a small number of degrees of freedom in general will not be log concave. So what if it's not log concave? Well, then we have to go to some of the other methods. And let's move to one of those, and one of them would be slice sampling, and which again is what BUGS will use in the case where the distribution only covers a finite range of values on the x-axis. So in those cases, it would use a slice sampler. Okay, and let me briefly describe that. Now, slice sampling actually is a little bit different in the sense that the previous two methods I talked about, inversion and the rejection sampling methods, generate independent random variables. A slice sampler isn't. It's actually a particular case of an MCMC sampling method. So it actually generates a sequence of random variables that are correlated with each other. So it actually generates, so you work with a sequence where you do a sample that is conditioned on some previous value. So again, it's an MCMC sampling strategy. In our case, again, we're going to talk about it in the univariate case. And it's relatively easy to implement this MCMC method in the univariate case. And let me describe that. To generate, again, some value, some random variable from some density f, but now it's going to be given some previous value that we'll just call x sub 0. This could either be an initial value, or we could be talking about a value just from a previous step where you've already run several of these. You generate a y. Now we're going to generate it not from a uniform 0, 1, but a uniform between 0 and the value of our density at our previous value, x0. And in fact, let me use the plot here as a way to orient you to this. So let's suppose that our density is this kind of complicated looking thing here. We've got a bunch of modes in it. And let's say we've got some initial value, x0. And we can calculate the value of the density at that. So that's our f of x0 in here. And now I'm going to generate a random variable along really the y-axis of this, so which is going to be some value between 0, I'm assuming this is actually 0 on here, 0 and f of x0. And all values between there are equally likely, so you'll generate such a value here, y. So here we've put such a value here on this. And then once I've got that value y, I want to generate my x uniformly on a sequence of values that might be disjoint, and they're described by this relationship. So A is the set of values of x such that f of x is greater than or equal to this value y, which sounds very math jargony, of course, but that's actually nothing more than a set of x's defined by taking a horizontal slice right through that function. So if we take y and we cut and we just put a horizontal line right across at the value of y, the places on here, right here, like here, here, and here, that slice right through this. Notice that for where I've sliced here, all values where this line falls below the function, and that's this thing that we're asking for here. So y has to be less than or equal to f of x here. So it's that set of values, and again we're going to assume all such values are equally likely, and we sample uniformly over that set of values here, and the value you get out of here is your next value of x. So that's the process then of doing a slice sampling problem. Now that sounds really simple, and when we talk about it graphically, it sounds almost trivial. The stinker here is discovering exactly what this set of numbers is turns out to be the hardest part of the problem, and the thing that you have to work hardest at if you're working with a slice sampler is to come up with an efficient strategy for basically discovering what the appropriate values are to sample from in step number 2 right here. Let's see, I think I've got at least one question that popped up here. Oh, no, I guess it hasn't. Or have we? Continue, middle. Okay, we're fine. Okay, so that's the technique then that is used by WinBUGS if the range of our, or actually I guess it's the support of our density is finite. So if you can sort of draw lines like this and say, okay, the density is 0 outside those bounds, then WinBUGS could tell that that's true, then it will usually use a slice sampler to do the univariate sampling in here. Okay, so those are the main univariate samplers. Now again, let me step back to our thing. What are we missing here? So we've done our well, we mentioned the inverse, we've mentioned the adaptive rejection and the slice sampling. As I say, if all else fails and it can't discover that the univariate full conditional obeys any of those for a particular variable, it finally resorts to a Metropolis algorithm, which actually covers a fairly wide range of algorithms, but I'll just give you sort of the description of kind of the plain vanilla Metropolis-Hastings algorithm, and then the specific algorithms are essentially all variations on the one I'll describe. Okay, so Metropolis-Hastings algorithm. Okay, it's a pretty general purpose and can be multivariate MCMC algorithm. but when we talk about it in the context of bugs, it's usually being used for the purpose of dealing with a univariate case. So the way I'll describe it, you can think of it either way you want. You can think of it as univariate or multivariate, and that's just a matter of how you interpret the y's and x's I talk about here. It requires selection of something called a conditional proposal density, and we're going to call it, and it's conditional, so it would be written in a form like this, where I've written it as Q of y given x. And you want this density to be easy to sample from. Okay, and so for example, if this was a univariate case for y and you had a value of x given, you want to be able to sample values for that y fairly easily. So you'd like it to be something nice, like a normal distribution, for example, for which you have efficient sampling algorithms. And then, now again, it's MCMC, so we're going to be working with a sequence of values. You have an initial estimate, and then you repeatedly step through to get multiple samples, but each time the next sample will depend upon the previous one. So the way I'll write this here is to generate xt plus 1, so it's going to be the t plus first sample from our distribution f. So I'm going to generate that, but I need and to do so, I'm going to be making use of the previous sample, the tth sample from that distribution that we call x super t in here. Well, the first step in that is I generate a number from that proposal distribution. And so the proposal is going to be written then as it's going to be again, I use that Q of y given x. So it's y given, in this case, it's given the previous value, previous sample, x super t. So we're going to generate a sample from that. And then we're going to, excuse me. And then we've got sort of a little decision thing here. So our next sample here, our x super t plus 1, is going to be, it will be either the y sub t or it's going to be the previous value. It's going to be y sub t with probability, here it says rho of x super t comma y sub t, and that quantity here, this function rho xy, is defined down here. So I'm going to take, well, the first, it's going to be the minimum of two values here. You take take our distribution f. We're going to have f at y or f at x. We take that ratio, and we also take the ratio for our q's, where again x and y reverse roles in that. And if that number is less than 1, that's the probability we would return over here. On the other hand, if this ends up being bigger than 1, we just return 1 in here. So, excuse me. So this is just going to be essentially a Bernoulli trial here. So you're going to be making a choice here, and it's going to be again y of t with probability, rho of x to the t, x super t, comma y sub t. Or it will just be the same as the previous value of x with the complementary probability, 1 minus rho. So so we go through that process and generate y sub t, decide whether or not to keep it or not. You either keep it or you keep the previous value, and then you move on, and in whatever value you have, it plays the role of xt here again, and you go through the process over and over again. Notice this is similar in some ways to the rejection sampling method, that we've got a test process here, but the difference is you're making a decision whether or not to accept y of t, but one of the differences is if you reject y of t, you don't just go through the loop again, you actually return a value. It's just that the value you return is exactly the same as the previous value. Now, the devil in the details here is going to be things like, is mainly associated with picking that proposal distribution and coming up with a proposal distribution that makes this reasonably efficient. And it turns out there's a whole lot of subtleties in that process. Because now, in the special case where the proposal distribution is actually identical to the posterior you're interested in, then this would be equivalent to just doing a standard sampling algorithm. It would, in a sense, no longer even be MCMC because the previous value wouldn't even play a role in those cases. But in general, that's not going to be true. You're going to have some messy F here that you're working with, and you're going to pick a not so messy proposal density to use to sort of approximate that. And the trick is to come up with one that's a reasonable approximation to the density that you've got, and coming up with a method for doing that. And then there's a variety of algorithms out there that attempt to do that in some adaptive fashion, where they go out and try to come up with some way of adapting Q. You know, you'll start out with some initial Q, and then you will try to sort of modify it. There'll be certain tuning parameters that may change, and in fact, when you work with WinBUGs, you'll see there's an adaptive phase within WinBUGs, and different algorithms have different techniques for trying to adapt and improve, and in particular, there's an adaptive strategy used that's associated with trying to improve that proposal density during the burn-in phase, but then it gets locked into place essentially once you start the actual post-burn-in sampling phase. Oh, let's see, is there really anything more I want to tell you about this in here? Not really directly, although I guess what I should do is point you to where you can find further information, because as I already said, that in all of these algorithms the devil really is in the details in terms of coming up with reasonably efficient methods. Let me actually step back to where I can get to the table of contents and point you to sources of information here. Okay, let me enlarge that again. Yeah, probably the two best, let's see, do I have both of them here or just the one? Let's see. Oh, it's the next page. Probably the two best books on this to get the real nitty-gritty here is probably this book by Robert and Casella that would give you lots of details on the various algorithms we've looked at. To look at it from maybe a slightly more practical point of view with less detail, but with some concrete examples, it would be the smaller book they published recently called Introducing Monte Carlo Methods with R, where they give you examples programmed in R for some of the different algorithms. You know, so both of them have their own strengths, and to some degree they're similar but complementary. But that would be the best resources, I would say, for looking at these, if you want to get into more details on it. Okay, let's go back up here. I think I'm using too much red there. Okay. Let's see, where are we going on time? Yeah, probably about right. Okay. Okay. Let's move past the algorithms and talk a bit about some of the computer programs that are out there. As I've already said, we're going to be focusing on using WinBUGs in the course, but I should make you aware of some other tools that are out there, and I sort of broke them down into sort of two broad classes here. One class of tool that's out there is some MCMC methods for Bayesian modeling have actually been added to what are probably some fairly familiar pharmacometric tools to many of you. And in particular, Bayesian methods have been added to non-MEM7 and SADAPT. Actually, it's essentially the same algorithm. It was originally put into SADAPT and then brought into non-MEM7. So it's actually got a fairly decent MCMC algorithm in it. And in fact, maybe at some point later on in the course, I'll actually show you a comparison of some results using both non-mem and WinBUGS. But at least, I guess just to give you sort of the bottom line is that in cases that where non-mem is really best designed, namely dealing with two levels of random variation, particularly in the case where the likelihood is also a normal distribution, non-mem actually does quite favorably relative to WinBUGS. But anyway, the advantages to tools like these is you've got PK/PD model libraries and model specification languages are already built into them. So they're already designed as pharmacometric tools. And one of the biggest advantages is that in addition to MCMC, there are less computationally demanding algorithms built into these programs. And the reason why I say that's a significant advantage is during the model development process, you'd often like a quicker algorithm that lets you run through and exclude a number of model candidates fairly quickly without waiting for very long computation times. So it's nice to have some of those less computationally demanding algorithms within the same platform rather than having to say do that work in one platform and then move on to something like BUGS for the next step. The main disadvantages is they're very limited in terms of the kind of stochastic model structure you can have. You're limited to two levels of random variation, plus the prior distributions in there. Now, of course, there are tricks to sort of describe a third level of random variation, but it's fairly restrictive to do that. And you're very limited in terms of your choice of distributions, at least for your inter-individual variation. And in particular, for inter-individual variation, you're limited to normal distributions, and you're limited to the normal Wishart combination for your prior distributions. So if your model can be described within those limitations, non-mem and SADAPT are both good options that you can use. The downside is the lack of generality in terms of model structure. Now, there are some more general purpose software tools that implement MCMC, and I've listed several here. There's only three that I have much direct familiarity with, and that's essentially the ones that use the BUGS model specification language. So that's WinBUGS, OpenBUGS, and another program called JAGS, which, believe it or not, is an acronym for just another Gibbs sampler. And the BUGS ones have been around a little longer. JAGS tends to be on average a bit slower, though the last version is an improvement. It tends to be a bit slower, but it has the advantage that it's more platform independent. In other words, whereas WinBUGS and OpenBUGS are for the most part restricted to a Windows platform, though there is a Linux version of OpenBUGS available. JAGS can port to pretty much anything that you can port C++ to, so that it's more general in that sense. But there are fewer add-ons that have been built for it, so it's a trade-off. And again, it's usually a bit slower for most complicated models that we deal with. There are some other tools out there that I'm not as familiar with. There is an MCMC procedure within SAS now. There's a package that Microsoft has called Microsoft Infernet, which is probably designed more around what are called Bayesian network strategies, but it sounds like it's actually a bit more general than that. Again, I don't have direct experience. There are a number of MATLAB add-ons that are capable of doing MCMC for various kinds of problems out there. Again, most of the comments I have here apply to the WinBUGS, OpenBUGS, and JAGS because they're the ones I'm most familiar with. The main advantages there relative to tools like non-mem and SADAPT is how flexible they are with respect to the stochastic model structure. There's no limit on the levels of random variation that you incorporate. You have a choice of a large number of distributions that you can use. It's also very easy to combine models that have very different stochastic structures. And that can give you a lot of flexibility for dealing with things like, combining things like models for in vivo outcomes, preclinical outcomes, clinical outcomes, where the things like inter-individual or inter-experiment variation mean very different things, and they would otherwise be very difficult to do in something like non-mem. Disadvantages is there's no built-in specialized support for pharmacometric applications, though as we'll see later I will provide you with some tools for doing that, so to some degree I've gotten around that problem. There's less flexible specification of your structural model, and in particular there's not like nice built-in for loops and if-then-else loops and things like that, and to get around those you have to do some custom programming that's a bit more difficult. And again, there's no less computationally demanding algorithms within the same platform. It'd really be nice if they had something like tools for doing maybe calculating posterior modes or something like that that could be done more quickly than full MCMC, but currently they're not built into those platforms. Okay, so again, the biggie here though is generality. So it's kind of that's your trade-offs when you look between things like between bugs and non-mem is non-mem. You've got the PKPD models built into it. You've got the availability of doing these sort of quasi-Bayesian. You can get essentially estimates of Bayesian modes and doing that more quickly. But BUGS is far more general in terms of the structure of the model. Okay, let's see. Hopefully we can do this in our remaining 15 minutes. I think for the most part we can, because what I want to do is set you off with an assignment to look at that we'll then go over on Friday. This is going to be sort of your first hands-on problem. But first I want to sort of set a framework. What I've done here is sort of constructed a fictional case study that will serve as kind of a running theme as we go through our hands-on examples in here. So as I say here, it's a fictional antithrombotic case study that we'll be using. So we're going to be looking at the clinical development of ME2, ME of course because it's Metrum. So we're going to be developing an orally administered direct factor 10A inhibitor that we've called ME2 for indications that include post-op prevention of VTEs, in other words venous thromboemboli, as well as prevention of thrombotic events in patients with atrial fibrillation. Our early clinical development is going to focus on that post-op prevention because that can be done a lot more quickly and with fewer resources, and it's generally believed that what you learn in terms of dose response there is still relevant to the atrial fib case. So again, and because it can be done more quickly and get basically more information from fewer patients and in less time, it's going to provide more exposure response information. Now, the size, duration, and variability and cost for atrial fib trials are quite large, making dose response studies pretty prohibitive during a phase 2 program in atrial fib. In phase 1, we're going to be looking at safety, PK, and biomarker PD. And our biomarker is going to be the inhibition of factor 10A activity. And that's going to be a biomarker both for efficacy and bleeding liability. Bleeding liability being our most likely dose-limiting toxicity for the compound. For our example, we're going to focus on inhibition of factor 10A activity and its relationship to PK by analyzing our phase 1 data. We're going to model the PK-PD relationship in a couple of different ways to illustrate both a simple nonlinear regression problem as well as a nonlinear mixed effects regression problem. Essentially, we'll use the same data both ways just so we can illustrate those two strategies. Now, another part of the story here is neutropenia was observed in some subjects receiving higher ME2 doses in phase 1, and we need to analyze that data further to assess whether there's sufficient probability of identifying a dose that's effective while still causing an acceptably small degree of neutropenia. And to facilitate that effort, we're going to model the relationship between neutrophil counts and drug exposure, and we're going to adapt the semi-mechanistic model proposed by Freiberg and Carlson. And in that one, we're actually going to be including the use of some informative prior distributions for parameters of that model that are thought to be drug independent. In other words, we'll be able to borrow information from the application of that model to previous drugs and use that information as informative prior distributions, thus really leveraging our Bayesian machinery here for that problem. And the clinical development plan includes a phase 2A proof of concept trial that compares one dose level of ME2 to an active comparator, which is enoxaparin, in patients undergoing total knee replacement. Our VTEs, the bleeding events, and PK are all measured, and we're going to analyze the combined phase 1 and phase 2A PK data using a population PK model. So all of that leads to the following sort of 4 core hands-on examples in here. So we're going to, though we've got these sort of core ones, some of these will actually be breaking up into sub-problems as we proceed through this. In addition, I may add a few additional problems as we go along, but most of what we'll be working with during this semester will be components of these 4 problems. First one we actually won't be breaking up, but the last 3 we will probably break them up into some smaller components to learn various elements of the analysis problem. But anyway, for our example 1, we're going to be analyzing a phase 1 study in healthy volunteers in which the PK and inhibition of factor 10A activity are measured. We're going to be doing a nonlinear regression of time average biomarker as a function of time average plasma drug concentration. And then for example 2, what we'll do is actually take the same data, but we won't time average it. What we're going to do now is do a direct action PK/PD model to the time matched biomarker and plasma drug concentration measurements, so that now the difference here, again in example 1, we've only got one observation per individual in a sense, because we've taken our multiple observations and averaged over them to create only one data point per individual, whereas in example 2 we'll retain all the individual data points, so now we'll have multiple data points per individual, and thus we're going to want to use a mixed effect strategy there. Example 3, we're going to be analyzing the PK data from phase 1 and 2 in there, and so that's a population PK modeling problem. And finally, our example 4 is we're going to analyze that neutrophil count data from phase 1 using that semi-mechanistic PK/PD model, and that's one where we get to illustrate a lot of things, such as 1, we're going to be using informative prior distributions. 2, we're going to be working with a model that's described in terms of a system of nonlinear differential equations, so we have to know how to work with those in the WinBUGS context. And in fact, these latter 2 problems are all going to be using a package that we call BUGSModelLibrary as part of the WinBUGS analysis. So let's get on to describing our hands-on problem 1. And in fact, this serves then as an assignment for you to be doing between now and Friday. During Friday's session, actually I keep saying Friday, it's actually Thursday, isn't it? Excuse me. During Thursday's session, I will then go through this with you. Okay, so our problem here then, we're going to be doing PK/PD modeling of time average biomarker and PK data. This comes from a phase 1 single dose study in healthy volunteers. That's a parallel dose escalation design. I've got 8 subjects per dose arm. I've got single doses of ME2 ranging here. You can see we've got placebo 1.255 and so on up to 80 milligrams. Our PK data consists of plasma concentrations of parent drug measured at the same times. Let's see. Oh, yeah, I haven't even said what those times are. Sorry. We'll get there. Okay, we've got plasma concentrations of parent drug, and our biomarker is ex vivo inhibition of factor Xa activity in plasma, and both are measured at the same times, and you can see they're measured at several times then over 24 hours following drug administration. The hands-on exercise is going to be modeling the relationship between the time averaged factor Xa inhibition and time averaged Me2 plasma concentrations. And by time averaged, I mean we'll take the observations over, so for instance, you take your plasma concentrations from 0 to 24 hours, take the area under the curve for each individual, and divide it by 24, and that would be our time averaged plasma concentration. And then do the same thing for the factor Xa inhibition. And frankly, that's an artifice just so that we end up with a single observation or a single metric or a single data point per individual to do a nonlinear regression. Here I've given you some pictures of the data here. On the left-hand set of panels, we've got the PK data, so we've got Me2 plasma concentrations versus time. I've just done spaghetti plots for all the different dose arms, and you can see the y-axes are different for each of these. So as we go up in dose, of course, the concentrations are actually going up. And then here we've got the corresponding factor Xa inhibition values here, so you can see it's factor Xa inhibition measured as percent inhibition. And again, we've got that plotted for all the dose arms. Here we've also got a placebo arm shown here. Here I've just plotted this a little differently. Here I've taken the factor Xa inhibition values and the plasma concentrations. I've matched them by time and plotted them against each other. And you can see, particularly as we get to the high doses where we cover the broadest range of concentrations, you can kind of see the shape of the exposure response. But again, this isn't the way we're going to model it on the first go. We're going to instead take the time average values, which is what I'm plotting here. So on this side, I'm taking my average factor Xa inhibition and my average plasma concentrations here, and I've plotted those. So each blue circle here is a single patient. Actually, these are normal volunteers in this case. In here, so you can see the shape of that. I've just overlaid on it a simple least squares curve that happens to be an Emacs model here, just to sort of give you a visual cue around the data points here, but you can sort of see the curvature happening here. And the model I'm going to propose you use is in fact going to be a sigmoid Emacs model, relating our time average percent inhibition of factor Xa activity to the plasma concentrations in each subject. Here I've used a subscript I for the individual subject. So I'm using E bar 24 to represent the time average factor Xa inhibition, and I'm using C bar 24 to represent the time average plasma concentrations. So I'm going to use so for our E bar 24 is going to have normal residual variation, so it's going to be normal with some mean E hat 24 and some variance sigma squared, and then our E hat is going to be described by our sigmoid Emacs model. So that's our core model here. We've got a residual variation as the only source of variation in here, but then we need to specify some prior distributions. And for this exercise, we'll start with some weakly informative prior distributions. Actually, you could say very weakly informative for this. Emacs here, I'm suggesting you use a uniform over 0 to 100. And I'd argue that makes sense here because we're talking about a percent inhibition in this thing. So it's pretty much, it certainly has to be restricted above by 100, at least for the average value. That would make sense. You could conceivably imagine that it could go below 0 if you wanted to allow for the possibility that instead of only causing inhibition, it might cause an increase. But for now, let's just assume that it either does nothing or it inhibits. So we'll restrict it from 0 to 100. I'm going to treat the prior for my EC50 as log normal, or equivalently the log of the EC50 is normal with some mean 0 and variance of 1,000,000 in this case. In other words, a standard deviation of 1,000, so that's pretty broad in this case. My gamma here, I'll just make it uniform 0 to 10. Basically, if you let it go above 10, you just end up with a square wave, and once you get to 10 and above, they all look pretty much the same. So there isn't much point in exploring values above that. And then finally, for the standard deviation, I'll use a uniform over 0 to 1,000 here. Again, there's other possible choices we can make, but those are the ones I'll suggest you use. Let's see, did I see a question pop up that I missed? Nope, I guess not. Excuse me. Then let me direct you to where these are on what you have. There's an example folder that's called ME Hands-On 1. The model, there's already a model in there. Actually, what I propose you do on this is don't start with the model itself. Let me, in fact, go down to that. Before we leave here, let me show you what's there. If you go down into your MI250 directory, there'll be an ME Hands-On 1 directory in here. And there's this ME Hands-On 1.odc in here. Let me fire up, before we go there, let me fire up WinBUGS. Okay, and let me go back and get that model in there. Okay, now there's actually the model already built in there, and in fact, in hindsight, I probably shouldn't have, excuse me, there we go. I probably shouldn't have given it to you that way. While I try to enlarge this a little. What I actually suggest you do is maybe go ahead and save this file under another name. Take this file and then just go through, just go down and delete the model. Just get rid of it and just keep the data and the initial estimate terms in here. Because for now I wanted to use this exercise mainly as one where you learn how to work with the WinBUGS interface and how you write the model. But we'll worry about data management stuff on subsequent exercises. So my suggestion to you is that you go ahead and go ahead and delete that and build the model yourself. So work with just a template with only the data in here and the initial estimates. And that's probably going to be the better learning exercise. Basically, it gives you a chance to make the mistakes in here. So the idea then will be to build the model, to write it in the BUGS language form. What I would actually suggest if you want a template to start with for the model is start with the linear regression model that we used for an example. And the main difference that you're going to encounter is that the function for the mean then, instead of being a straight line, is going to be that sigmoid Emax function. So that will be different, and then of course you have a different set of variables that you have to specify priors for. But the overall structure of the model would be essentially the same, at least in gross terms. So that's the task I'm going to set out for you then, is basically learn how to work with the WinBUGS interface, learn how to construct your own model, and use this the hands-on one example is the basis for doing that. Let me take a breath, and we're actually gone past our official time, but I can take some time for any questions if anybody has any, and then I'll just wait till Thursday. Okay, well, I probably put everybody to sleep here. Nothing's popping up here right now, so I guess I will go ahead and say goodbye for now, and look forward to talking to you again on Thursday. So bye for now.